Alex, can you explain the difference between 444, 422, and 420? What we're talking about here is called chroma subsampling. And if your eyes just glazed over, don't worry. I've got some simple diagrams. In a couple of minutes, you're going to understand this perfectly. There's a lot of confusion about this topic, primarily because there have been two different systems for chroma subsampling over the years. And they can be written out the same way, like 420, but they mean different things. I'm not going to get into all those details today. I'm just going to go over the most modern and prevalent system for chroma subsampling and the way it's written out today. Let's start at the beginning. An electronic image is composed of pixels. Pixels can have a couple different attributes. One is called luminance, luma, which tells the pixel how bright or dark to be, and chrominance, chroma, which tells the pixel basically what color to be. If you take all the chroma out of a picture, you're left with a black and white image. But if you take all the luminance out of an image, you're left with no image at all. Now, to have a reasonably good picture, each pixel does need to have its own luma data. But a few decades ago, some pretty smart engineers figured out that each pixel does not need to have its own chroma data. You can force chunks of pixels to share the same chroma data, basically to be the same color, and still have a pretty good image. Now, how many pixels you force to be the same color basically determines how much chroma subsampling you're doing. Let's take a look at this in a little more detail. The conventional formula for writing out the chroma subsampling ratio is like this, JAB. The first number, J, tells us how many pixels we're dealing with. How many pixels wide is the reference block for our sampling pattern. Sometimes it's 8 or 3, but usually it's 4 pixels wide. The second number tells us how many pixels in the top row, the A row, are going to get chroma samples. And the third number tells us how many pixels in the bottom, the B row, are going to get chroma samples. As you can see here, if every pixel in the 4x2 grid gets a chroma sample, there's actually no subsampling going on, and the scheme is 444. That's what's used in high-end HD cameras like the Panavision Genesis and Sony f35. Now let's take a look at 422. We're still dealing with a reference block that's 4 pixels wide. That hasn't changed. But now, every 2 pixels on the top row, the A row, have to share a chroma sample. And every 2 pixels on the bottom row, the B row, also have to share a chroma sample. We've definitely lost a lot of detail, but we can still get a good idea of the original image. This is the subsampling used in Panasonic cameras that record in DVC Pro HD, and Sony cameras that record in XDCam HD 422, as well as in editing codecs like Apple ProRes 422. So this is still a very good image. Now let's take another step down and look at 420. We're still dealing with a 4 pixel wide reference block, and our A number is still 2. So every 2 pixels on the top row still share a chroma sample. But the B number is 0, which means that the pixels in the bottom row don't get anything of their own. They have to share with whatever's above them. You can really get an idea of how much information, how much detail is being lost here. And this is the chroma subsampling used by DV, HDV, Apple Intermediate Codec, and most flavors of MPEG, including the ones generated by Canon DSLRs. Looking at this diagram, you can see one of the main reasons why formats with heavy chroma subsampling give you blocky artifacts. What you're seeing is actually chunks of pixels that are sharing chroma data and being forced to be the same color to save space. This really becomes an issue when you talk about pulling a chroma key. Think about trying to pull the green pixels out of a shot of smoke or wispy hair. It'd be pretty easy if each pixel had its own chroma sample, like this. But it gets much harder when pixels are sharing samples, because the green pixels aren't necessarily at the exact edge of the image anymore. That's why you get those jagged lines around the edges of chroma keys with subsampled footage. Now, there are a lot of factors that contribute to the quality of an image, and chroma subsampling is only one of them. I'm going to address some of those other issues in future videos. Well, I hope this has been helpful. If you want to see more videos, visit 5dfilmmaking.com. And if you have a question for me, send it to the address on the screen. See you next time.